That is a nice cold beer. It's my 1-year anniversary on YouTube, so I wanted to celebrate by making a fun video and having a couple beers. So I decided to try to make an instant beer cooler. Okay, it won't really be instant, but my goal is to make something that can chill a can or a bottle to a really nice cold temperature as quickly as possible. I think I've got an idea that should work pretty well, so let's jump in and see how well it turns out. Please remember, likes and subscribes really help the channel grow so we can keep the content coming. I love to see your comments down below and I'll try to answer any questions. And if you want to help us directly, you can do that over on Patreon, where you also get bonus content and behind the scenes videos. I think submerging the can in cold liquid is going to give us the fastest results, so I'm going to go in that direction. The first thing to consider is how the heat transfer actually works in this situation, so that we can take advantage of the physics and leverage that to make the can as cold as possible as quickly as we can. So in submerging the can, we can take advantage of conduction and convection. Conduction is when heat is transferred directly through contact. So if we can get really cold water surrounding the can, the cold water will suck out tons of heat from the can. And convection is when heat is carried away by a moving fluid, like wind cooling your skin on a breezy day. So if we can make the water swirl, we can cool the can even faster. So we want the fluid surrounding the can to be as cold as possible to leverage conduction, and we want it to be constantly moving to leverage convection. Next, we want to look at how to get the surrounding fluid as cold as possible so that the temperature difference between that fluid and the can is as great as possible. The larger the temperature difference is, the faster the can will cool down. I'll be using a water-based solution for the cooling fluid, so one thing I want to look at is how I can reduce the freezing temperature of the water so I can get the water even colder than 32 degrees or 0 Celsius without it freezing. Moving water prevents freezing because the constant motion disrupts ice crystal formation, like how rivers stay liquid longer than still ponds or lakes in the winter. So by keeping the water moving, we should be able to drop the freezing temperature by a few degrees, maybe to 28 or 30 degrees Fahrenheit before it begins to freeze. And then we can introduce additives like salt, sugar, or glycol, which act like an antifreeze and lower the freezing point by interfering with the water molecules bonding into ice. At a 20% solution, salt can drop the freezing temperature to about 22 degrees Fahrenheit, sugar to about 28 degrees Fahrenheit, and glycol to about 23 degrees Fahrenheit. I'll give a quick demonstration of this in action. I'll set up 2 buckets side by side. First, I'll mix in enough salt to make one of the buckets a 20% salt solution. Now I'll add the same amount of ice to each bucket, and then I'll measure the lowest temperature that both buckets get to. 33 minutes in, and you can see that the saltwater bucket is at negative 9.4 and the plain bucket is at 0.7. So this bucket is over 10 degrees colder, and it's even forming a band of frozen condensation on the outside, whereas this bucket's nowhere near cold enough to freeze on the outside. So this demonstrates just how much colder we can get the salt water to go than the plain water, and it worked even better than I expected it to. Now getting into the actual design. After considering a bunch of different ways to make cooling, I think I'm going to go with Peltier modules. So this is a Peltier module, and the first thing I'll do is stick a heat sink on one side so that it doesn't overheat, because the hot side can get too hot really quickly without one of these. So next, I can just plug it in to this DC power supply. As soon as I give it power, the module is going to start transferring heat from this side to this side. So this will get hot and this side will get cold. Peltier modules are thermoelectric coolers that use electricity to pump heat from one side to the other. There's no moving parts or refrigerants, just efficient heat transfer. They work by passing current through semiconductor materials sandwiched between ceramic plates, creating a temperature difference where one side gets cold and the other gets hot as electrons carry heat across. And then I'll unplug it. So now I need to use the Peltiers to actually chill the water. When heat or cold are transferred, it's actually the heat energy moving from the warmer object to the cooler object following the laws of thermodynamics. Heat always flows toward the lower temperature to reach equilibrium. So the Peltiers accelerate this by actively pumping the heat out of the water and into the surrounding air via heat sinks. So I'm going to use a block cooler to assist in the heat transfer. Inside this, there's an M-shaped channel that the water has to flow through, creating a lot of turbulence and prolonging the amount of time that it spends in the cooler. I can attach the Peltier modules directly to this with thermal paste to give really good contact between them and the water flowing through it. I'll use a pump to circulate the water through this cooler and back into the bucket where the beer will be. Okay, now we can get into the actual build, and I might have to experiment with it a little bit along the way, but this is the rough setup. There's going to be a bucket that has a fluid swirling in it that you put the actual drinks into, and then just through some hose, it'll go to some heating blocks with Peltier modules and heat sinks that should hopefully cool the fluid down to a really low temperature, and a pump is just pushing it in a loop through the whole system. So there's a lot of monotonous work to get through to get the build together, and there's a lot of wiring and little things to do. So I'll jump through all that and be right back. Now I'll start getting the heat exchanger assembled, and this will probably be pretty messy and chaotic, but it's pretty simple in concept. So the center heating block will be for the cold water, and so the cold side of the Peltiers will face that. And then those get sandwiched by two more heating blocks, and these are to shed the heat from the Peltiers. And then just for some extra heat shedding, these will have heat sinks. Basically, it's just a big sandwich, and then I just need to tighten it down to keep it all together, and that is basically the heat exchanger. So I'll be using thermal paste, and this stuff is probably going to get pretty messy, but we'll see how it goes. With the heat exchanger and its power supply put together, I'm getting really close. Now I'm just going to hook everything up with some silicone tubing and test it and see how cold I can get the water. Okay, it should all be hooked up, ready for the test. This is the actual beer cooling bucket here. And it's hooked up to the center cooling block, and then these two buckets are hooked up to the outer ones just to keep the whole heat exchanger cool. And then here is a temperature block. So first I'll turn on the pumps and make sure everything's circulating well, and if that's looking good, then we'll turn on the heat exchanger and see how fast it cools down. Okay, it's looking pretty good. The water's moving in all the buckets, so I can tell the pumps are on. I don't see any air bubbles trapped, so I think I've probably got good flow. And now I'll go ahead and turn on the Peltiers and see what happens. The heat sinks are 18 degrees, so that's great. That should be plenty cool enough to really drop this temperature, and you can see it's starting to come down now. Okay, so it's just about 10 minutes in, and it's dropped about 5 degrees, so it's definitely working. But one thing I need to do is add some insulation to this bucket. Okay, so we're 20 minutes in, and we're down to 1.3 degrees Celsius. Okay, that was pretty good for a first test, but it started to plateau right around freezing, which will get a beer cold pretty fast, but I want to try to get it quite a bit colder than that so that it's a lot faster. So now I'll just try to tweak the system to make it more efficient. I'm going to tighten up the insulation. I'm going to get this up in the air and get a fan on it. I'll try to shorten the hose runs and get them insulated just to really max out what this system can provide. So I put this within a bigger pot and stuffed it full of insulation, so hopefully the pot is a lot more insulated. And now I'll just try to tweak the rest of it. Okay, everything's ready for test 2. I'll put the insulated lid on top, and we're starting at about just under 9 degrees Celsius. So first I'll make sure that the pumps all run and the Peltiers are on. And I've got a fan on that. I've also added a liter of glycol to the cooling fluid this time. I'm using food grade glycol this time because it won't be corrosive to the metals like salt would. It's getting close to where the last temp maxed out, but it achieved it much faster, so the system is working a lot more efficiently this time. Okay, we seem to have slowed down at -3.4. I don't know if it's a plateau, but let me show you this. There's a solid layer of ice built up on the central cooling block. The glycol solution might be becoming more viscous as it cools down, slowing down the flow, which could explain the plateau in temperature. So the beer is 19 degrees Celsius, and in we go. All right, 2 minutes in, and the beer is 14 degrees. Let's do 2 more minutes. And we're down to 6 degrees. I'll do 1 more minute. We can see that the temperature's gone from negative 3.4 to negative 2.4. And that represents the heat being transferred from the can into the surrounding water while the can gets colder. Okay, so 5 minutes in the cold, and we're down to 4.8 degrees. 6 minutes, and it's at 3 degrees Celsius. That is a nice cold beer. So basically the system works. I think it's a little underpowered, especially if you wanted to do beer after beer. I think doubling the Peltier system would make a massive difference. The thing would cool down so much faster, and you could do drink after drink after drink, and I think it would probably keep up pretty well. You'd also be able to shorten the cooling time probably to just a couple minutes. The average person is obviously not going to build something like this, but something we learned from the saltwater demonstration is that if you want to cool down a bunch of drinks really quickly, add a bunch of salt water to a cooler and then dump in a ton of ice, and you can get it down to around negative 10 degrees Celsius. The salt water also increases the conduction a little bit, so the cans will cool off even faster, and I think you could cool down a whole ton of cans really quickly. So maybe if it gets really hot again, I'll work on doubling this and make a nice custom cabinet enclosure for the whole thing. But it's probably time to get back to some real work. Thanks a lot for wasting your time with me on my YouTube anniversary. This one was a lot of fun, but kind of pointless. Thanks a lot. I'll see you again soon, and take care.